Hello everyone, you're watching at present functions of several variables. You are most welcome, and we are taking here directional derivatives. Let this R be the set of real numbers. Then Rn we can write R into Rn times. This equals to this tuple, n tuple, we can say n tuple of values x1, x2, xn, where each xi belongs to reals. This function, let S be the subset of this Rn, and function S to Rn, this is called real valued function of n variables. We have considered here x1, x2, xn, these are reals, and this is known as function real valued function of n variables. For taking n equals to 2, then function, this is subset S, goes to R2. This function f is called a real valued function of two variables. The set S is called the domain of this function, and the subset of R is range of the function. A function f of two variables x and y is a rule that assigns a unique real number fxy to each point in some set S in the xy plane. So in n-dimensional space in which a point is a sequence like this way of n real variables x1, x2 up to xn, and a function of n real numbers is a rule that assigns a unique real number fx1 up to xn to each point in the same set in this space. Now we are talking about directional derivatives. Directional derivatives, let us consider two-dimensional plane x and y. This is origin. Let P and Q be two neighboring points in this two space, or we can say two-dimensional space. This PQ makes a theta angle, an angle theta with the positive x direction. Then angle with the y-axis will be pi by 2 minus theta. Now direction cosines of this line PQ, also known as DCs, will be cos theta and cos pi by 2 minus theta. So DCs will be cos theta and sin theta. Now let us consider a point PAB. PAB is here, and Q, neighboring point of this Q, P is Q. So this Q is A plus H, comma B plus K. And let us consider direction between these neighboring points P and Q is L. So by Pythagoras theorem, L equals to H square plus K square. Square root of L equals to square root of H square plus K square. And H upon L, by trigonometry, H upon L equals to cos theta. Therefore, H equals to L cos theta. Similarly, K equals to L sin theta. Now, if we consider Q tending to this point P, Q reaching at position P, then this distance L tending to 0. This distance L tending to 0. Now, if taking limit tending to 0, function at position E plus H, comma B plus K minus function AB upon L, on putting the value of H and K from here, H equals to L cos theta, K equals to L sin theta, we have limit L tends to 0, f E plus L cos theta, P plus L sin theta upon L, and this one. This is known as directional derivative of function fxy at the point E comma B. It is denoted by d theta, directional derivative in the direction of theta of function f at point AB. Now, if we assume theta equals to 0, if theta equals to 0, then result will be directional derivative at theta equals to 0, that means x direction of function f at point AB equals to limit L tends to 0, function E plus L cos 0, comma B plus L sin 0 minus f AB upon L. Similarly, we can assume for different values of theta, we will obtain directional derivative at that point. Now, if we consider a function of 3 variable and unit vector is given in this form, u1 I cap plus u2 j cap plus u3 k cap, then directional derivative of function at point ABC. So we are considering here function of 3 variables. So directional derivative in the direction of unit vector u is partial differentiation of function at point ABC into u1 plus fy ABC u2 plus f z ABC into u3. fx, fy, fz. These are partial derivatives of function at point or at given point ABC. Here in the direction of unit vector u cap, DC's are u1, u2, u3. These are direction cosines. And in above formula, DC's are cos theta and sin theta. Now partial derivative of f at point ABC, or we can say fx at point xyz, gives the slope, the tangent line to a surface in the positive x direction. Similarly, fy and fz gives us the slope of tangent line to a surface in the positive y direction and z direction. Now we will consider some examples for finding directional derivatives. Find the directional derivative of fxyz given by this. This is function of three variables. Variables 3 are x, y, z. At the point, these are points we can take ABC or scalar points 1, minus 2, 0 in the direction of the vector. Vector is given 2i cap plus j cap minus 2k cap. If this vector is not unit vector, then we will normalize this vector by using a vector upon magnitude of that vector. So it will becomes like this: 2 upon 3 I cap plus 1 upon 3 j cap minus 2 upon 3. So this one will be our u1, u2 and u3, or we can say a1, a2 or a3 accordingly. And if here we are using formula second, if these are du f abc fx, this formula we will use for finding directional derivative, or as per our choice we can use also this type of formula. So directional derivative of this unit vector of function f at point ABC is given by fx abc u1 plus fy u2 plus fz u3. We will use this formula for finding the directional derivative at a point ABC. Now we will use this one as u1, this one as u2, this one as u3, or we can write this one as a1, this one as a2 and the minus 2 upon 3 as a3 is our requirement. For the purpose, because function is given fxyz is this one, x square y minus yz cube plus z. So this is function of three variables, and if a function of more than one variable, then we will use derivative partial. We differentiate that function partially with respect to one variable and treating remaining, if any, variables or variable as a constant. So here we will obtain del f del x, this one or this one, or we denote this one or we denote this one. So this is partial differentiation of the function with respect to x. While differentiating this function with respect to x, we are treating other variables y and z here as a constant. So del x, this term, this term, this term. If here we are differentiating with respect to x, so 2x into y, because y is a constant, we are differentiating partially. Here with respect to x and treating yz as constant, so differentiation of yz cube with respect to x partially is 0. Similarly, partial differentiation of z with respect to x will be 0. So this is fx at x, y, z equals to 2xy. Now we will obtain the value of this partial differentiation at point 1 minus 2, 0, because we want to find the directional derivative at this point. So 2 into x equals to 1 here, and y is minus 2 is here. Simplification gives us minus 4. Similarly, fyz, this is the fy partial differentiation of function with respect to y, and the value of fy at the given point is this one. Similarly, fz will be this one. Now directional derivative at 1 minus 2, 0, denoted by du cap, function at point 1 minus 2, 0. On putting all the values in the given formula, we obtain minus 4, this is fx at minus 1, 2, 0 into 2 by 3 u1, plus 1 into u2 value is 1 by 3, minus 1 into u2 value is 2 by 3. Simplification gives us this minus 3 result. Now let us consider another example. Find the directional derivatives du cap fxy of the function f equals to this one in the direction of unit vector makes an angle of pi by 3 in the positive x-axis. Also find du cap f 3.434. So in this problem, angle is pi by 3 with positive x-axis, okay, and function is of two variables, okay. Unit vector, this is unit vector given here, so unit vector makes an angle pi by 3. Unit vector for this problem will be u cap cos pi by 3 I cap plus sin pi by 3 j cap, and function is given this one, partial differentiation, because this function is of two variable, So we will differentiate this function with respect to x, treating y as constant. So this is the result, and this is the partial differentiation of function with respect to y is this one. So according to problem, directional derivative of f at xy is fx u1 and fy u2. Here u1 is unit vector is given directly, therefore we will not normalize this one. We are putting directly, this is direction cosines and this is direction cosines for pi axis, as we have discussed. So we will use cos pi by 3 and sin pi by 3 as u2, and this is fx value from here, and fy value is here. Simplification on putting the value of we will obtain. Also du f34 on putting the value of x equals to 3, y equals to 4. Simplifying result we will obtain minus 94 minus 5 to 5 root 3 by 2. Now these are some practice questions you can solve easily. Find the directional derivatives of function this one at the point p11 1 in the direction of the line. Here line is given x minus 1 upon 2, y minus 3 upon minus 2, z upon 1. Directional derivative at 1 1 1, answer will be 35 upon 3. You can solve this easily and find the directional derivative of the function this one at point 1 2 3 in the direction of the line PQ, where P is the point 504. In what direction it will be maximum? Also find the magnitude of this maximum. So directional derivatives of f is the direction. This is the answer, 4 under root 21 upon 3. And directional derivative of f of is maximum in the direction of the normal to the given surface. So surface will be this one. And value of this surface, maximum value, is 2 root 41, square root of this one. These are some practice questions you can solve easily. If facing some problem, then you may discuss. Thanks for watching.